Okay, hi everyone. Let's start doing homework number 3 for CHEN 422, Chemical Reaction Engineering. This homework has 7 problems. It will be assigned on September 8th and it's due a week from that day, which is September 15th. So let's have a look. The chapter we talked about this week, we're talking about ideal reactor design. So before we start, let me just start off by summarizing or giving an overview of what you really need to know to solve problems, right? So again, this is week 3. It's chapters 4 and 5 from Levenspiel, which is the book I am following for this course. The reading material has been posted on Blackboard. And in this chapter, we basically looked at ideal reactor design. And we looked at 3 reactors. The first one is your ideal batch reactor. Which is referred to as IBR. And the performance equation for this batch reactor is T is equal to Ca note, integral from 0 to XA final, dXA over minus RA, and this is equal to as well minus Ca note to Ca of dCA over minus RA. And if you recall what a batch reactor is, it is a vessel which I just charge, and then after some time passes, I take out the product. Okay. The second reactor we covered was the CSTR, or your mixed reactor, or continuously, maybe this is a U here, X or something, continuously stirred tank reactor, right? And this is usually referred to as CSTR. You will also, it's also listed as a mixed reactor, so a lot of the times it's written as a mixed flow reactor, right? And the performance equation for this reactor is V divided by FA0 is equal to is equal to tau over Ca note is equal to XA over minus RA, right? And again, a CSTR, and this is the general expression. In your slides, we also derived the expression for a first order irreversible reaction in a CSTR, and for a first order irreversible reaction, the equation was tau K is equal to XA over 1 minus XA is equal to Ca note minus Ca over Ca, right? Good. And for a CSTR, this is the CSTR. So again, it's a vessel. It's always mixed. However, I'm charging a feed and taking out the product all the time. So this is the second type of reactor here. And the third type of reactor we talked about is a PFR. So the third type of reactor was your plug flow reactor, PFR, right? And the equation for a PFR we said is V over your volumetric flow rate. This is equal to tau. and this is equal to CA naught integral 0 to XAF of dXA over minus RA, and this is also equal to minus CA naught dCA over minus R. So these are the three performance equations you have to be aware of. And again, a PFR, as we said, it's unmixed. So unlike the other two, the PFR is unmixed. And we're just assuming that it's just elements just plugging, pushing each other through the reactor. There's no mixing in the direction of the flow. Okay, and this is the PFR. A few terms. So you see here we have a bunch of parameters. Let me just define a few terms before you move on. So Ca is your concentration, right? It's in units of mole per volume. T is time, right? Xa is your conversion. And we said for a conversion, the equation for conversion is Ca is equal to Ca naught, 1 minus Xa. Alternatively, you can say that Xa is equal to 1 minus Ca over Ca naught. This is your reaction rate. And depending on the order of the reaction, the units will change. V here is the volume of the reactor. Fa naught is your molar flow rate. And this is in mole per time. Tau is your space velocity. And it's in second. And space velocity refers the amount of time it takes one volume of the reactor to zip through the reactor. Any other expressions here? No. So these are the space velocity, just be aware of it. V naught here, this is your volumetric flow rate. And this is in units of volume per time. And a few good conversions to remember besides, so we have these two equations. There's always good tools to have. It gives you some flexibility. Other useful equations are, tau is equal to V over volumetric flow rate. What else? Let's see. Fa naught is equal to Ca naught V naught, right? So this is mole per time. This is mole per volume. This is volume per time. This is also a very useful equation for you. It gives you some flexibility depending on the given to arrange things and then do some math. Okay, so these are the basically this is the gist of this chapter. All right. On your exam, besides the theoretical stuff you see in the slides, so at the beginning of your slides, we have a comparison between all three of them. You're responsible on how to solve or how to use these equations to solve problems, similar to what we're going to talk about in a second in this one. Okay, so let me go to the homework. So let me go to the homework. It's homework 3, and let's have a look at problem number 1. So problem number 1 here, and move this guy to the second screen here. Problem number 1, you're given a gaseous feed. Ca0 is 100, Cb0 is 100, A plus B goes to R plus S. Xa is equal to 0.8, and you're asked to find Xb, Ca, and Cb. Okay, what happened here? Resume share. Okay, so I have a gaseous feed. Ca0 is 100, Cb0 is 100, A plus B goes to R plus S, Xa is 0.8, and you're asked to find Xb, Ca, and Cb. Okay, so let's go to the whiteboard. And so I saved this, I think. Clear all my drawings, and let's start solving problem number 1. Okay, so this is number 1. You're told a gaseous feed, so and you're given Ca0 is 100, Cb0 is 100, A plus B goes to R plus S. So 1 mole plus 1 mole gives me 1 mole plus 1 mole. So there is no change in volume because it's a gaseous feed. If you had a different number of moles, then you need to correct for the volume, but for this case, there isn't any change in volume. You're given also XA is equal to 0.8, and you're told to calculate XB, CB, and CA. Okay, so this is sort of a simple problem. Let's start with CA, because I have XA and CA note, so I can calculate CA using this expression, basically the definition of conversion. So CA is equal to CA note 1 minus XA. This is equal to 100 into 1 minus 0.8. This is equal to 20. Okay, so I have CA. What about CB? Let's think for a second. So this is a 1-to-1 reaction. So if N moles of A reacted, this means that N moles of B reacted. So if Ca note minus Ca, this is the number of moles which reacted, the initial number of moles of A minus the final number of moles of A, this is equal to Cb note minus Cb. So here I have 100 minus 20 is equal to 100 minus Cb. So in this case, Cb is equal to 20. And once you have Cb and you have Ca note, I can calculate Xb, which is equal to 1 minus Cb over Cb note. And this equation is the same as this equation, just rearranged. And for B, not A, is equal to 1 minus 20 over 100. And this is equal to 0.8, right? 0.8. So we got XB, CB, CA. This is number 1 done. Okay, let's go back to the homework and have a look at number 2. And number 2 is the exact same as number 1, except in this case, CB0 is 200, right? So gaseous feed CA0 100, CB0 200. No. Find XB, CA, CB. So it's the same problem, but CB now is 200. Okay, let's. This is a very simple, really type of exercise, but you just need to be cognizant of these, of these little things, really. Okay, let's have a look at number 2. Am I sharing the correct screen? Sorry. I am. Okay, let's have a look at number 2. So number 2, it's the same as number 1. So let's just rewrite it again, doesn't matter. A plus B goes to R plus S. We're given CA0 is 100, CB0 is 200, XA is 0.8, XB is what, CB is what, and CA is what. Okay. So same approach. I'm just gonna mirror the steps and plug in a different number, right? So CA is equal to CA note into 1 minus XA, and CA will be 20. And similarly, because it's a 1-to-1 reaction as well, so CA note minus CA is equal to CB note minus CB. In this case, 100 minus 20 is equal to 200 minus CB. So in this case, CB will be 120, right? 200 minus 80, 120. So I have CB, and then finally I'm going to calculate XB, 1 minus CB over CB note, 1 minus 120 over 200, which is 0.4, right? 0.4, so you have XB. Okay, so this is number 2, very simple problem. Let's move on. Let me save the screen, and let's clear all my drawings. Let me go to the homework, and let's have a look at number 3. Okay, now let's start solving some interesting problems. Okay, number 3. In an isothermal batch reactor, 70% of a liquid reactant is converted in 30 minutes. What space-time and space velocity are needed to achieve this conversion in a plug flow reactor and in a mixed flow reactor? Okay, so I have a batch reactant with a liquid reactant. Sorry, I have a batch reactor with a liquid reactant. 70% of the reactant is converted. So X, let's call it A, X is 0.7. And the time of conversion is 13 minutes. You're being asked what's the equivalent space-time and space velocity in a plug flow reactor and in a mixed flow reactor. Okay, let's go back to the whiteboard. Let's try to strategize or see what's the deal with this problem. Okay, so this is number 3, right? So in this case, I'm told I have a batch reactor. I'm told that it has a liquid species. Let's call it A. XA is 0.7, and T is equal to 13. And you're asked to find the tau for CSTR and the tau for a PFR. Okay. To achieve the same thing. To achieve basically the same conversion. So let's just write down the 3 performance equations, right? So performance equation for an IBR, we said T is equal to CA naught 0 VXA, sorry, 0 to XA, zero to XA of dxa over minus RA. Okay. For a PFR, tau is equal to CA naught integral 0 to XA dxa over minus RA. And for a CSTR, the performance equation was what? I think it was tau over CA naught is equal to XA over minus RA, or basically tau is equal to CA naught XA over minus RA. Okay, so let's have a look at these equations. So I know that when you compare these equations, and we discussed this at the end of the last lecture, you find out that these equations, the design equations for an ideal batch reactor and a PFR are the same. And the reason for this, we said, is because a PFR, there is no mixing in a PFR in the flow direction. So you can think of a PFR as a bunch of small batch reactors just pushing each other. That's why these equations are the same. So because these equations are the same, so the time for the IBR will be equal to the tau for a PFR, and this will be equal to 13 minutes. Okay. Now let's have a look at this at the CSTR here. CA naught XA over minus RA. So this really depends on the kinetics, right? So this parameter here depends heavily on the kinetics. And because I don't have the kinetics, implies tau cannot be calculated, right? And you have to have the knowledge to just say that, I don't have enough information to get tau because, there's this equation requires a number here for me to plug in. Okay, so this is the answer for this problem. So the space-time required for a PFR is the same as the time for an ideal batch reactor. Whereas for a CSTR, we cannot calculate the CSTR. So tau CSTR cannot be determined without the kinetics. Okay, so this is number 3. Let's go back to homework. Share. Let's share our homework again. I just posted. Right. Right. Okay, let's share our homework. So now we're doing number 4. In problem number 4, you're being told we plan to replace our present mixed flow reactor with one having double the volume. Okay. For the same aqueous feed and the same feed rate, find the new conversion. The reaction kinetics are represented below, and the present conversion is 0.7 or 70%. So I have a system with an aqueous feed, moles per liter. I'm on a conversion 70%, and you have the same feed rate, and you're given some reaction kinetics. You're being asked to find the conversion if I double the volume, right? So we plan to replace mixed flow reactor with one having double the volume. Find the new conversion. This is really the problem. Okay, let's go to the whiteboard and let's just have a look at this problem. So I'm going to clear all drawings and let's use the color this time. Okay, so this is number 4. So I have my original reactor. So original mixed flow, original CSTR. Okay. And this one has a volume, let's call it V1 for the same aqueous feed. So you're given Ca note 1 is equal to 10 mole per liter. And the same feed rate. So feed rate basically means Fa note 1 is equal, and you're told the same Ca note 1. So here is same feed rate. Fa note 1 is equal to Fa note 2, and Ca note 1 is equal to Ca note 2. And I'm gonna call this 1, and then my new situation, new CSTR. It's just a bigger tank, right? And V2 is equal to 2V1, right? So replace our present reactor with one having double the volume, and Ca2 is the same as Ca note 2 is the same as Ca note 1. Fa note 2 is the same as Fa1. And you're being told that Xa1 is equal to 0.7, and you need to basically find Xa2. And you're given some kinetics. So what are the kinetics? You're given the reaction happening is A goes to R, and the kinetics is minus RA is equal to K Ca to the 1.5. Okay, this is all the given. It's a CSTR. Sounds good. So let's try to solve this problem. Okay. So because it's a CSTR, the first step logically would be to let's write down the CSTR performance equation. Okay, so let's write down CSTR. Sorry, there's an E here. And the CSTR performance equation we said is what? Let me bring it here. We said V over Fa0 is equal to tau over Ca0 is equal to Xa over minus Ra. So I'm just going to use this side and this side. So the equation I'm using really is going to be V over Fa0 is equal to Xa over minus Ra, right? Okay, so let's try to calculate this, or let's try to plug in these parameters for both the original and the new. So for the original case, I have V1 over Fa note 1 is equal to Xa1 over minus RA1. I'm going to plug in this expression here. Before plugging it in, let's just rewrite this in terms of CA0, because this is the parameter I'm given, right? I'm given the CA0, I'm not given anything about CA, or you can calculate CA, but let's just write it generally. So this is equal to K into CA0 into 1 minus XA to the power of 1.5. And recall that CA is equal to CA naught 1 minus XA. This is the definition of the conversion. So I have this expression which I can plug in directly here, right? So I'm going to plug in this expression directly here. So I get basically is equal to XA1 over K into CA naught 1 minus XA1 to the power 1.5. So this is the equation for the original reactor. You can plug in the numbers here if you want. I don't like to plug in numbers until the very end. For the new CSTR, I'm just going to rewrite the same thing. V2 over FA naught 2 is equal to XA2 divided by K CA naught 2 1 minus XA2 to the power 1.5. Okay, so let's call this this line extends. Hopefully, doesn't cause any confusion. So I'm gonna call this equation 1, and I'm gonna call this equation 2. So now I'm gonna divide 1 by 2, right? 1 by 2. So on the right hand side, I'm gonna get V1 over FA naught 1 over V2 FA naught 2 is equal to XA1 over K CA naught 1 1.5 1 minus XA1 1.5 divided by XA2 over K CA naught 2 1.5 1 minus XA2. Actually, I didn't need to do this, but you know, it's fine. 1.5, right? So these are my two expressions. And from here on, it just becomes an algebra problem. So let me save this screen. And let me give myself some space on this side to continue the math. Okay, so I'm going to take it from here to this side. Now let's see, before moving on, let's just have a look. So I could possibly cancel, this with this, right? I can cancel this K with this K. I can cancel CA naught 1 with CA naught 2 because they're the same. And I end up with a really boiled down expression, which I just need to solve. So let's write down our final expression here. So you have V1 over V2 is equal to X1 over 1 minus X, or XA1 to the power 1.5 divided by XA2 over 1 minus XA2 to the power 1.5. Okay, sounds good. So what do I do now, right? You're given in the problem that XA1 is equal to 0.7, and you also know that V2 is equal to 2V1. So let's plug these guys in here. So I know that V2 is equal to 2V1. So basically this means that V1 over V2 is equal to half, right? So I'm going to have half is equal to 0.7 over 0.3 or over 0.3 to the 1.5, right? So I have 0.7 over 0.3 to the 1.5 over xa2 divided by 1 minus xa2 to the 1.5. Let me cross multiply, to get rid of this fraction from the bottom. So you're going to end up with xa2 over 1 minus xa2 to the power 1.5 is equal to 2 into 0.7 divided by 0.3 to the power 1.5. Okay, and from here on, it just becomes an algebra problem. If you have a calculator, you can do it with a calculator. 0.3 to the power 1.5, and this is equal to 8.5. So I need to find xa2 over 1 minus xa2 to the 1.5 to be equal to 8.5. And you can iterate. If you're very fancy math, you can probably do it, just do a bunch of fancy math, but we're just going to, so what I did, you can use a calculator. What I did is I just plugged in, I plugged in XA to be 0.8, and I plugged in XA to be 0.7, and I just, narrowed it down by just iterating, and the answer I got for XA2, answer I got for XA2 was 0.79. Okay, if you have a calculator or these TI calculators, you can use Excel to do it. Whichever way to do it, just figure out a way to solve these types of algebraic problems, which are not straightforward, right? Are not cute, basically. Okay, so this is the end of problem 4. So the answer is, if I double the reactor volume, my conversion is going to increase from 0.7 to 0.794. Good. So this is problem number 4. Let's move on to number 5. Okay, so number 5 here. It's you have an enzyme E catalyzes the fermentation of substrate yes, we're told enzyme E catalyzes the fermentation of substrate A to product R. Find the size of the mixed flow reactor needed for 95% conversion of reactant in a feed stream and enzyme. The kinetics of the fermentation of this reaction are given. Kinetics of fermentation at this enzyme concentration are given below. Okay, so you're given a reaction A goes to R. You're given an initial concentration, 25 liters per minute. You're given a conversion of 95%. And you're given also a volumetric flow rate, and you're given a bunch of kinetics. And you need to find the volume of the mixed flow reactor. Find the size. So you need to find the volume of the mixed flow reactor. So let's translate all of this given onto the whiteboard here. Let me share a new whiteboard. Let me clear all my drawings and let's start. Okay, let's start. So this is number 5. And let's first of all start by just drawing our problem, right? It's the easiest thing, or the first thing you always need to do. You're given a reaction, A goes to R, and you're given a minus RA is equal to 0.1 Ca over 1 plus 0.5 Ca, and the units of this is mole per liter minute. So find the size of the mixed flow reactor. So you need to find volume of a CSTR, which achieves the conversion of XA 0.95 in a feed stream, and you're given a feed stream V naught is equal to 25 liter per minute with an initial concentration Ca naught is equal to 2 mole per liter, right? So these are all the givens. And again, you can draw a little diagram if you want, you know. Here you go. You know, this is the feed, this is the given, etc. So I know it's a CSTR. First step, write the CSTR performance equation, right? CSTR performance equation, we said it's V over FA naught is equal to tau over CA naught is equal to XA over minus RA. Okay, sounds good. So I need basically FA naught and I need minus RA to get V, right? Because I already have XA. So let's start with FA naught. So FA naught is equal to CA naught multiplied by V naught, right? This is mole per liter. This is liter per minute. So I should get FA naught in mole per minute. So CA naught in this case is 2. V naught is 25. So my FA naught is 50 mole per minute. Okay, minus RA, you're given an equation, which is 0.1 CA over 1 plus 0.5 CA. We need CA to do this. So in order to get CA, you need to recall that CA is equal to CA naught into 1 minus XA. This is equal to 2 into 1 minus 0.95. And this is equal to 0.1, right? 0.1. So I know that CA is equal to 0.1. I'm going to plug 0.1 here, 0.1 into 0.1 over 1 plus 0.5 into 0.1. And what do I get? I get this number, which is 0.0095, right? And this is in units of mole per liter. Let me separate these guys. Okay, so I have minus RA, I have FA naught, so I'm just going to plug all of these numbers here. So this implies that V is equal to FA naught XA over minus RA. This is equal to 50 into 0.95 divided by 0.00952. And this will be equal to 484987. And what are the units here? Let's just double check the units. This is mole per minute. This has no units. This is mole per liter per minute. So this is basically liter. Okay, so this is the answer for the problem. So this is the size of the CSTR required to meet the given metrics. And again, you know it's a CSTR, write your CSTR performance equation, find out what's missing, find it, and then plug in. This, and you need to just something to note that I can only plug in the numbers for minus RA in the case of a CSTR. If you have a PFR, you have a IBR, you need to integrate. You can't just plug in numbers and use it, right? For other reactors, you need to integrate. For the CSTR, I don't need to integrate because this is the performance equation. Just plug in the numbers and find the reaction rate at the given concentration. Okay, number 5 is done. Let me save this drawing and let's go back to the homework. Let's have a look at number 6. Number 6. So we finished number 5, right? Have a look here. Number 5 is done. Let's have a look at number 6. An aqueous feed containing A with 1 mole per liter enters a 2-liter plug flow reactor and reacts away using this equation. Find the outlet concentration of A for a feed rate of 0.5. So you're told you have a PFR with a feed at a concentration of 1 mole per liter. The volume of this PFR is 2 liters. And in this PFR, I have this reaction happening. And you need to find the outlet concentration of A for a feed rate, volumetric feed rate of 0.5 liters per minute. So I need to find CA basically. Okay, let me go back to my whiteboard. Let me clear all my drawings. And let's start doing this problem. Okay, this is problem number 6. Number 6. Let's write the given. So I have a PFR. Aqueous feed containing A with a concentration CA naught is equal to 1 mole per liter. And this is a PFR, right? Enters a 2-liter plug flow reactor, and volume of this PFR is equal to 2 liter. Reacts away using this reaction. 2A goes to R, and minus RA is equal to 0.05 CA squared. And the units are mole per liter second. Find the outlet concentration of A. So I need to find CA for a feed rate of 0.5 liter per minute. And you're given a volumetric feed rate of 0.5 liter per minute. Okay, first step, I'm going to write the performance equation for the PFR. So let's write it. So the performance equation for a PFR is V over V naught, and this is equal to tau, is equal to CA naught integral from 0 to XAF of dXA over minus RA, and this is also equal to minus integral CA to CA naught of dCA over minus RA. So because I'm given everything in CA, I'm not given any conversion, so I'm not going to use this form. I'm just going to use this form of the equation, okay? So let's focus on this, on this right-hand side. So I have V. Actually, let's write it properly to avoid confusion. So I have basically V over V naught is equal to minus integral CA naught dCA over minus RA. I'm going to plug in the equation for minus RA. So this is equal to minus CA to CA naught of dCA over 0.05 CA squared. And if I go all the way to the top here, so I have V over V naught is equal to minus 1 over 0.05 integral dCA over CA squared from CA, or from CA naught to CA, right? These boundaries are wrong. From CA naught to CA, from initial to final, that makes sense. Just be careful about these things. CA naught, just make sure you catch it at some point before plugging in numbers, right? CA naught to CA, and this expression here is equal to minus 1 over 0.05, and the integral of 1 over x squared is minus 1 over CA from CA naught to CA. Okay, so this is the expression. So now let's plug in numbers. So I know V over V naught is equal to minus 1 over 0.05. And this will be minus 1 over CA minus 1 over minus 1 into CA naught, right? So I just plugged in my limits of this integral. CA naught was 1, so this is equal to minus 1 over 0.05 into minus 1 over CA minus 1 over 1. And basically this becomes V over V naught is equal to minus 1 over 0.05. Let's just calculate this because we're going to get a clean number, right? This is 20 is equal to minus 20 into minus 1 over CA plus 1, right? Plus 1. And now let's have a look at this guy right here. So I know V is 2 liters, V naught is 0.5, so this is equal to 4, right? So I have basically, 4 is equal to minus 20 into minus 1 over CA plus 1. If I rearrange a few things, so I'm gonna divide 4 by minus 20, so I'm gonna get what? 4 by minus 20 0.2, so I have minus 0.2 is equal to 1 minus 1 over CA. So if we just do the math, 1 over CA is equal to 1.2. So CA is equal to 1 over 1.2, and this is equal to 0.833. And this is the answer to this problem. Of course, the units are mole per liter. So you're being asked to find the outlet concentration, and this is the outlet concentration, and this is how we solve this problem. And again, similar approach. You're given a reactor, given a bunch of conditions, given a reaction rate, write your performance equation, work through the problem, and find your number, okay? Most of the errors, if you do an error here at the very beginning, then you didn't understand the problem. Read the problem slowly, make sure you absorb all the information, and then try to practice your algebra. Sometimes, a lot of times, just drop a number here, drop a minus sign here. This is very common. Just try to be aware of your calculations. Try to be avoid being sloppy, especially with your writing, so that you don't drop any parameter. Okay, so this is number 6. Let's move on to number 7. Let's have a look at number 7. Okay. Number 7, an aqueous feed of A and B, 400 liters per minute, 100 millimoles per A, per liter, 200 millimoles of B per liter, is to be converted to product. The kinetics of the reaction are represented by A plus B goes to R, and minus RA is equal to 200 CA CB. Which flow reactor type will require the smallest volume to achieve a 99.9% conversion of A to product? Okay. So you're given a situation where I have an aqueous feed of 2 species, A and B. I'm given a flow rate, volumetric flow rate 400 liters per minute. I'm given an initial concentration of A of 100, an initial concentration of B of 200, and I'm given a reaction rate kinetics. And you're being asked to find which reactor, the PFR or the CSTR, will require the smallest volume or the smaller volume for this reaction to achieve a 99.9% conversion. Okay, so a lot of this is not a straightforward problem. Let me clear. Save it. Okay, let me clear all my drawings, and let's start working on this problem. Okay, number 7. So in this problem, I'm given. When you have comparison problems, I highly recommend you don't plug in numbers until the very end. Okay, it's up to you, whichever way works for you, but this is how I would do it. So in this situation, I'm given a reactor. I don't know if it's a PFR or a CSTR. I need to do the comparison. In this reactor, I have a reaction A plus B going to R, and the reaction rate in this case minus RA is equal to K, CA, CB and you're given that K is equal to 200, it's fine. And entering this reactor, I'm given a CA node, I'm given a CB node, I'm given a V node, and I'm given an XA. Okay, and you're given numbers for all of them. So this one is 100, this one is 200, this one is 400, right? And this one is 0.999. So you're given numbers for all of these. We can write them here if you want, or actually I don't want to write them, it doesn't matter. So I need to find V PFR versus V PSTR. Which one is smaller? So let's start with the PFR, okay? PFR, and I'm going to start with the performance equation. So the performance equation for a PFR says V divided by V naught. This is equal to CA naught integral 0 XAF dXA over minus R. Okay. If you recall from last week's slide, we did a similar type of integration for case, I think 2, second order reversible reaction. And this is what this is, a second order reversible reaction. Because if I plug in my numbers here, I'm gonna get basically what? I'm gonna get CA naught integral 0 XAF dXA KCA CB. So I need to rearrange this in a way where I have conversions of XA. So let me write something. So I'm gonna minus RA is equal to K CA CB. You know that CA is equal to CA naught into 1 minus XA, right? This is the definition of the conversion. And I know that CB is equal to CB naught into 1 minus XB. We also know that, you know, because it's a one-to-one reaction, so n number of moles of A reacting will be equal to n number of moles of B reacting because it's a one-to-one. So this means that CA minus CA naught is equal to CB minus CB naught. And looking at these equations, this means that basically XA CA naught is equal to XB CB naught. So I'm going to rewrite this expression as XB is equal to, or actually, yeah, we're going to rewrite it as XB is equal to XA CA naught divided by CB naught, right? Or if you want, you can say that XA is equal to XB CB naught over CA naught. And now because these are constants, I'm going to define a parameter M. And we did this last week in last week's slide, and this is normal practice just to avoid writing this fraction everywhere and you're going to make an error. So I'm going to say let M is equal to CB naught divided by CA naught. Okay? So taking all of this into consideration, let me plug all this information into this reaction rate right here. So I have minus RA is equal to K. Instead of CA, I'm going to write CA naught 1 minus XA. And instead of CB, I'm going to write CB naught 1 minus XB. Okay? So I'm going to distribute these guys into these equations. So I get K CA naught minus CA naught XA multiplied by CB naught minus CB naught XB. Okay? And then I'm going to use this fact to replace it here. So now I have K into CA naught minus CA naught XA into CB naught minus CA naught XA. And this is because XA CA naught is equal to XB CB naught. So I just made this substitution. Okay. Now going here, I'm gonna take CA naught out. So I get minus RA is equal to K CA naught into 1 minus XA. And I'm gonna take CA naught out of this guy, CA naught into CB naught over CA naught minus XA, and CB naught over CA naught is M. So basically this expression becomes K CA naught squared 1 minus XA M minus XA. And we've seen this expression before in last week's slide, so be aware of the substitution. If you see a second order reaction and you want to plug it into here, you can jump to this conclusion directly if you want, or if you really want to do the math every time, you can always do this derivation just to reassure yourself. Okay, so this is minus RA. So I got to this point, that's fine. So now let me plug it into this expression, right? So I got this far, and now I'm gonna plug it into this expression. So let's go to the top here. So I have V over V naught is equal to CA naught integral 0 to XAF dXA over K CA naught squared into 1 minus XA into M minus XA, right? Oh, this is integration by parts, no, not parts, fraction. You need to split the fraction, right? You need to break the fraction. So let me rewrite it. So I have V over V naught is equal to CA naught over K CA naught squared. You can cancel this guy with this guy, of course. 0 XAF dXA over 1 minus XA M minus X. Okay, so at this point, I need to break this into two fractions before moving any further. So I'm going to save this page, and now let me erase all of the stuff here so that we have some space to work. Okay, sorry. So I need to split this fraction. So I have 1 over 1 minus XA into M minus XA, and I'm gonna split it into A over 1 minus XA plus B over M minus XA. If I do this algebra, I'm going to get, I'm basically going to get with, if I basically combine these two guys, I will get A into M minus XA plus B into 1 minus XA over 1 minus XA M minus XA. And this has to be equal to 1. So now A into M minus XA plus B into 1 minus XA has to be equal to 1. So I'm going to take the two extremes when XA is equal to 1. So this is 0. So this means that A is equal to 1 over M minus 1. And on the opposite side, when XA is equal to M, this means that B is equal to 1 over 1 minus M. So I have A and I have M. I can rewrite this fraction as follows. So basically my integral now becomes, let me save, then let me clear this side. Okay, so now my integral, so if I take it, so let's write it actually. Yeah, let's just take it to this side. So now I'm doing this v over v naught is equal to 1 over k ca naught integral of 0 xaf of a over 1 minus xa, so it's what? 1 over m minus 1 multiplied by dxa over 1 minus xa plus 1 over 1 minus m of dxa divided by m minus xa. Good. So this is my my integral. Let's just integrate this expression. So I have v over v naught is equal to 1 over k ca naught, and let me just draw a big bracket. This is equal to what? Minus 1 over m minus 1 ln 1 minus xa, right? Minus 1 over 1 minus m ln m minus xa, right? And this I'm substituting from 0 to xaf. And this is correct. Just, double check your math, make sure you remember the stuff. And practice it. Okay, 1 over kca naught. I'm going to substitute these numbers in here. So I have minus 1 over m minus 1 ln 1 minus xaf minus 1 over 1 minus m ln m minus xaf, right? And then I'm going to have a minus of minus 1 over m minus 1 ln 1 minus 0 minus 1 over 1 minus m of ln m minus 0. Okay, so this is my expression. So this one, ln of 1 is 0, so this guy goes to 0. This is just ln m. So if I just take 1 over 1 minus m out, so I have v over v naught is equal to 1 over k ca naught. And I'm going to take 1 over 1 minus m out. If I do this, I'm going to end up with ln 1 minus xaf minus ln m minus xaf minus ln m. So this is my expression so far. Let me save it up until this point. Save, and let me erase from here, and let's that we can continue on this. And we're still calculating, trying to get an expression for the volume of a PFR. So if I just plug in all of this stuff, I'm gonna get V over V naught is equal to 1 over K CA naught into 1 over 1 minus M. And I'm just going to get the combined expression. So, this will give me what? This will give me wait. Yeah, this is correct. I'm just double checking my signs. Did I mess up the sign? Because this is not match what I have here. Okay, so I have 1 over KCA naught. I took 1 over 1 minus M out, right? So I get ln of 1 minus XA minus ln M minus XA. Sorry, and this is what? So this is going to be a plus. Wait, is this correct? One second. Let's just double check what we're doing here. Minus 1 over 1 minus M. Minus 1 over M minus 1 minus 1 over 1 minus M. So this is basically equivalent to 1 over 1 minus M, right? This is 1 over 1 minus M minus 1 into the 0, and then minus this guy minus this, and this becomes plus. So this is plus. So if I take 1 minus M out, this has to be plus. Right, this has to be plus right here. Because if I take 1 over 1 minus M out, this is plus 1 over 1 minus M. Okay, this makes sense now. So this becomes ln. I'm gonna just combine all the lns together. So this will be M into 1 minus XAF divided by M minus XAF. And this is similar to the expression we got in the last slide. So remember one thing, just ln A plus ln B is equal to ln AB, right? And ln A minus ln B is equal to ln A over B. Okay, this is just a mathematical thing if you forgot it. Just a reminder. So I have this expression right here. So now what is the volume of a PFR? So the volume of the PFR will be equal to, I'm just going to move this V naught inside, will be equal to V naught over K CA naught into 1 over 1 minus M into ln of M into 1 minus XAF over M minus XA. So this is the equation for a PFR for a second order reaction. You can use it directly if you want on an exam. But if you just be aware of how it's being derived, because the same approach applies for other orders as well. Okay. So I have it for the PFR. Let's have a look at the CSTR now, right? So the performance equation for a CSTR is V over FA naught is equal to XA over minus RA naught. And I'm going to plug in the same expression for minus RA, which I derived at the beginning of this problem. So this is equal to XA over K, CA naught squared, 1 minus XA, M minus XA. Okay? This is the performance equation for a second order reaction in a CSTR. Okay, so now I'm gonna just rearrange these expressions. So FA naught is V naught multiplied by CA naught, right? So just recall that FA naught is equal to V naught CA naught. If I do this, so and I cross multiply, so I'm gonna get V is equal to V naught CA naught over K CA naught squared multiplied by XA over 1 minus XA M minus XA, and if this cancels with this becomes the volume of the CSTR. So I have two equations, one for the volume of a PFR, one for the volume of a CSTR, and the problem is asking you which reactor will require the smallest volume. Okay, so now I have both equations. I can plug in numbers, I can compare them directly. No, not what I want to do. Anyways, let's go this way to figure this out. Okay. Come on. Okay. Finally, let's use green. And let's move to the side. So I'm going to move here and I'm going to write them again. So the volume of a PFR is equal to V naught over K, CA naught, 1 over 1 minus M, ln of M into 1 minus XAF divided by M minus XAF. This is as opposed to volume of a CSTR, and this is equal to V naught over K, CA naught into XA over 1 minus XA, and M minus XA. So basically what's going to determine which reactors is smaller, because these two are the same, is this part of the expression, right? So this part and this part. If we recall from the given, we're told that XA is 0.999 and M is equal to CB naught over CA naught. And this is 200 over 100. This is equal to 2. So let's calculate the volume of a PFR is equal to V naught over K CA naught 1 over 1 minus 2 ln 2 1 minus point over 2 minus point, right? And this number is going to give me what? Sorry, so I get what? 2 multiplied 1 minus 0.999 divided by point of answer. Divided by minus 1, right? So here I get 6.215 V naught over K CA naught. So this is this expression for the PFR. The expression for a CSTR will be V naught over K CA naught XA is 0.999 over 1 minus 0.999 multiplied by 2 minus 0.999. And in this case, I'm going to get I'm going to get a very large number actually, and this is 998.0 V naught over K. Okay, so from this, it's clear that the PFR will give me the much smaller volume, right? One thing to note about the volumes of PFR versus the volume of a CSTR is as X increases, so as X increases, the volume of the CSTR increases significantly compared to the volume of a PFR, right? And this is something to remember as you're, maybe training for the exam or just thinking about these things. Is that, as XA approaches 1, maybe this is a better way to say it. As XA approaches 1, the volume of the CSTR increases at a much higher rate than the volume of a PFR. As you can see here, if 0.999, can see that this difference is huge. So I mean, we're done with the homework, but I'm just going to say something here. So if we just have a look at these parameters, just for your comparison, So if I'm just taking a look at these parameters here, so if I go here and I say, when XA is equal to 0.999, I find out that the volume PFR is 6.215 V naught over KCA naught, and the volume of a CSTR is 998.0 V naught over KCA naught. If I do the same calculation for XA is equal to 0.99, let's try to do this calculation for the same M. So same M, don't worry about it. So I'm gonna get 2 multiplied 1 minus 0.99 divided by 2 minus 0.99, then answer. And in this case, this is equal to 3.92 V naught over K CA naught, and this number is equal to 0.9 divided by 1 minus 0.9 divided by 2 minus 0.9. This number is equal to 8.18. Sorry, it's 0.99, right? So 0.99 divided by 1 minus 0.99 and divided by 2 minus 0.99. This number becomes 98, right? So here I get 98.01 V naught over KCA naught. And as you can see, this difference now significantly dropped, right? So now if XA is equal to 0.9, you'll find out that for a PFR, it's 2.47 V naught over KCA naught, and for a CSTR, it's 8.18 V naught over KCA naught. You can see that, now it's only 4 times. Here it's much higher. Now let's try XA is equal to 0.7, see if it flips. So 2 multiplied by 1 minus 0.7 divided by 2 minus 0.7, 2 multiplied by 0.7 divided by 2 minus 0.7, equal answer. So in this case, I get 0.773 V naught over KCA naught, and for a CSTR, I get a 1.79 V naught over KCA naught. So here it's double. Is there a crossover point? Let's try and do this just out of curiosity. 2, 1 minus 0.5 divided by 2 minus 0.5, and then answer. So this is 0.405 V naught over KCA naught, and in this case 0.5. And in this case it's 0.66. And as you can see, as the conversion decreases, they're getting closer. But if you need much higher purity, you'll find out that a PFR is much more efficient, right? So at very high purities, PFR is significantly more efficient. As your purity requirement drops, they sort of start behaving, or your volume requirements are. Okay, this is the end of homework 3. It's due a week from the 8th, so due on the 15th. If you have any questions, please come to office hours, send me an email, and let's talk, let's meet, let's try to understand this. Okay, thank you very much.